the crimes which are not crimes using laws that are not existent. In the last 2 weeks, there were close to 10,000 people in Russia who were attacked on streets just because they do not agree with unlawful arrests. I could be one of those people. You can do anything.
Alex?
Yeah.
Alice, we could not see your screen. Could
I
you
guess
say again?
That's because I was banned from this conference.
Yeah, it appears now.
So, yeah, we can now go to the more important stuff like competitive programming. So, in problem A, you were asked to find which people can we hire such that it will be it will have the most total cost. Like we kind of should solve assignment problem, but we are not given the matrix. So we have to find which people can be assigned with some matrix according to the M permutations that were given to us. And the number of people was pretty big, but the number of positions was very small. And the solution for this problem is that let's look at some matching, and let's assume that let's look at the matching such that we do not take the best person for any position. So we took some people, but we do not take the best person for any one position. Then I state that we can do better. We can find a matching that is strictly better, so we do not move to the right in any position, but we will move to the left in some position. And actually, we can always take at least on at least one position. We can take the best person for this position. Why is it true? Well, because we can draw edges like for each person that we took. We can draw a directed edge to the person which is the best for this position. And in this graph, we can either find a chain from some taken person to the not taken person, and then alternate this chain, or there will be a cycle, and we can alternate using this cycle. So there should be at least one position for which we choose the best possible option. We can try all these positions. There are M of them. And then we know that we take the best person for this position. We remove the position, we remove the person, and proceed recursively. So this will work in time m factorial times some polynomial of m. And if it is implemented something like that, it might not pass. Actually, we're trying all the permutations of positions, and then for positions in this order, we choose the best not already chosen person. The stupidest way to implement that would be m factorial times m squared, because we have m factorial permutations. Then for each permutation, we go through m positions, and for each position, we might have to check m persons. But if we try all the permutations recursively, then it will be m factorial times m, and this one should pass pretty easily. This one can pass, but only if written very optimally. If you have questions about problem A, you can ask them now. Okay, then we will move to problem B. Problem B was about a game where we had 22, at most 22 problems. For each problem, we know its score. And the game proceeds as follows. We have two players. In each turn, both players somehow, probably using some random distributions, choose a problem. If they choose different problems, then the game stops, and the result of the game is the score of the problem the first person choose. And if they choose the same problem, then this problem removed, and we continue. If there are no more problems left, the score is 0. It is easy to see that the state of the game is fully described by the set of problems remaining. So we have 2 to the n masks. And in each such state, we can just basically play some small game. For each problem, we know what will be the resultant score of the game if we have chosen this problem and our opponent did not choose this problem. This is just the number from the input, and we also have we also know what will happen if we choose this problem and our opponent also chooses this problem. This is like the result of GP with smaller set of problems, like after removing this one. So it is already calculated in GP earlier. So now we, for each problem, we know these two numbers, and we should make the best move. So this is a game not in usual CP sense, but in like game theory sense. We have to choose. We have to use minimax theorem for games with mixed strategies, which says that the result of the game can be calculated if we force one of the participants to choose his mixed strategy in advance and then communicate it to the other player. So if the first player chooses his strategy in the optimal way, it doesn't help the second player to that he knows the strategy. So the strategy is the probability distribution on our actions, and action is what problem we should choose. So let's find the strategy for our opponent, which is the best for him. So his strategy is described by this vector of probabilities. The sum of all the probabilities should be 1, and all the probabilities are non-negative. After that, if he chooses the problem, then we will get BI if he chose the same problem, and if he doesn't choose the problem, we will get AI. So for each problem, we can now calculate like its real cost as the probability that it is not chosen times AI plus the probability that it is chosen times BI. And obviously after that, if we know this strategy, we will just choose the problem that has this value as maximum, because we want to maximize the score. So we have to calculate what is the minimum value over probability distribution P we can get of maximum of these values. Okay, this problem is kind of solvable in a general case, but we can use some statements we can get from the fact that these values are the values we get from the game. So the first statement will be if we have two numbers such that AI is less than AJ, then let's say less or equal, then BI would be greater or equal than BJ. Why is it so? Well, it is easy to see that if we take some game with sorted AIs, or not sorted, it doesn't matter, and increase some of them, but not decrease any of them, it is clear that the result of the game should also not decrease. Because we can take the optimal strategy in the game with smaller AI and apply it to the game with bigger AI, and we should get not result not worse, because in any case, like in any engine situation, we will get at least as much points. So what are the numbers BI and BJ? It is what will be the value of the game if we remove AI from it, and BJ, what will be the value of the game if we remove AJ? So if we remove AJ, which is greater than AI, we will get a game which is like strictly worse. Not strictly, but all AIs are not bigger than AIs in this game, so it should has a worse result. So that's one of the properties. And the second property is that for the largest AI, let's say that AIs are sorted, then AN should be at least BN. Why is that? Well, BN is a result of the game from which we removed AN, but that means that all the remaining A's are not bigger than this one. And in the end of any game, we will get either 0 or some of the one of the AIs. All of them are not bigger than AN, so some weighted sum of them with weights sum into 1 should be also not bigger than that. So the result of the game from which we remove the maximum value is not bigger than this maximum value. So knowing these two facts, we can solve this problem a bit more easily than in general case. Let's look at these numbers. What we know, like the nth one, we have an and we have bn somewhere to the left, like it is smaller. So what will happen when we change pn, the probability? If it is 0, then we can get this value. If we will increase it, we will slowly move to the bn. So let's look at all the other values. We know that they are sorted, like we have chosen it like that. We have sorted them. Like the actual situation will look something like that. And in some point, we can get that sum A is actually smaller than B we get. So let's start with P all equal to 0, and then we will increase some of them such that we decrease the maximum of these values as much as possible. So we start at all of these points, and we can start to move them towards the B counterparts. Since we have at least one such option where AI is at least BI, it doesn't make sense to move this because we will only increase the values, but we can also spend, we can always spend all the P here. So we will basically set some tokens here and start moving them to the left. And when we have spent the sum of P becomes 1, or we found this point where we cannot move to the left, we can only move to the right, we stop. We can spend, like if that happens, so we have moved all the letter here and we have not reached the sum equal to 1, it is still smaller, we have to make it equal to 1, but we can always take the last one and move it to the left until we get the needed sum. So this process can be implemented in linear time. We don't have to sort AIs all the time because we can sort them once in advance. So the whole solution works in 2 to the n's times n. Do you have questions about problem B? Okay, then problem C. In problem C, you were asked to calculate the number of sequences of length n minus k, and k is not very big compared to n. So the sequence is at least 3n over 4 in length. The elements should be from 1 to n, and the property we're looking for is that the sum in every non-empty subset is not divisible by n. You could know kind of famous problem which asks you to find the like given an array of length n, it asks you to find the number of the subset which has sum divisible by n. And this problem is solved by calculating prefix sums and saying that we will always have two prefix sums that are equal, and we can take the segment between them. Its sum will be divisible by n. We will try to apply the same logic, but now our array is shorter. So what we want to prove? We want to prove that there should be a number that appears many times. What is the idea? Like how are we going to do that? We can calculate prefix sums for any order. So we will choose some order of elements in our array and then try some different orders such that we can somehow prove that we can, in some of the order, we can get a subsegment with sum divisible by n if we don't have enough equal elements. So let's say that the x is the most frequent element. And the number of elements that are not x is t. It is well known that we can construct a minimum of n minus k divided by 2 and t pairs of not equal elements from our array. So the number of pairs, not intersecting pairs that are that consists of two different elements is minimum of like half of the elements and t, because in every such pair there should be at least one number which is not x. Okay, great. So let's construct these pairs. We don't know the fixed array. We just saying that let's take any array that is good, and we can always construct that many pairs. Let's then reorder the elements of our array such that it starts with t pairs, and then some other elements. Like in this picture, it means that all of the elements that are here are x's, because it looks like t is smaller than n minus k over 2. So we have t pairs and then all the different elements. Then let's calculate the prefix sums. If some of the prefix sums are equal modulo n, then we can take a segment in this array, in this order, and we will get a set with sum divisible by n. What we can also do is we can swap the elements in one of the pairs. What will happen to prefix sums? Like, let's take the pair that is not the first one. All the prefix sums that are here will not change. All the prefix sums that are here will also not change. The one prefix sum that will change is here, between these two elements. And it will always change because these two elements are different. And we can actually do this for any of the pairs independently. So let's write down all the prefix sums that we had initially, and also the t prefix sums that we can get additionally here if we swap the elements. We can, if any of these numbers are coinciding modulo n, then we can actually construct the array such that we have both these prefix sums and take a segment between these prefix sums, thus getting a subset with sum divisible by n. So the number of prefix sums we could get is n minus k plus 1 plus t. That's just the number of prefix sums in the initial array, and we can also construct t more. So if this is at least n plus 1, then we will surely find two equal prefix sums. And there couldn't be. So from this we can deduce that T should be here T is this minimum. So yeah, let's write it. Let's call this Y. So yeah, if it is at least n plus 1, it is bad. So it should be at most n. Which means that Y is at most k minus 1. So since k is at most n over 4, it couldn't be that Y is n minus k over 2. So actually T should be at most k minus 1. Which means that the number of occurrences of number x is at least n minus k minus t, which is strictly greater than n minus 2k, which is at least n over 2. So this is the main fact about this problem. You could have guessed it. After that, the problem is not that hard. If we have numbers that occurs at least n over 2 times, then it should be k-prime with n. Otherwise, we could just take enough of them. So GCD x and n should be 1. So there are phi of n numbers of ways to choose x. If we choose x, then since x is co-prime with n, we can divide everything in the array by x, and it won't change the fact that the sum of some subset is divisible by n. So now x is equal to 1, actually. So the number of arrays, and yeah, since we have at least n over 2 elements x is unique, and it is uniquely defined by the array, and vice versa. So we can take all the solutions with x equal to 1 and then multiply them by any number which is co-prime with n. So the answer to the problem should be phi of n times the answer if x equal to 1. So now we have to calculate the number of arrays that at least n over 2 elements of them are ones. And also there is no subset which sum is divisible by n. So all the other elements should be strictly smaller than n over 2, because otherwise we can take enough ones with this one element to get the sum equal to n. And now if we just take them in any order and start adding them up, we start with 0, like adding them up. If we have reached something that is greater than n, we can find the first place where like this number is greater than n. So this is greater than, that is at least n. Let's take this prefix with this sum. It is at least n over 2, because this jump was at post n over 2, and we get something that is greater than n. So this subset has some at least n over 2, and we can add enough ones to get some equal to n. So this cannot happen. So the sum of all elements that are not ones should be at most n. Then obviously the sum of just all elements in the array should be strictly smaller than n. And obviously, any such array is good because then the sum of any subset will be strictly less than n and obviously not divisible by n then. So we are okay with any array with sum strictly smaller than n, and it is a well-known problem. We can prove with stars and bars method that the number of such arrays is choose n minus 1 k minus 1. So the answer is this multiplied by phi of n. This is the answer to the problem. And you can actually calculate it just in linear time. Like this is in square root of n time, and this you can calculate by taking n minus 1 times n minus 2 and so on, and 1 times 2 times 3 times something here. You will have k multipliers in the numerator and k multipliers in the denominator. So calculate them in k time. So this is just 2k multiplications, and time limit was 4 seconds. So it should pass easily. Do you have any questions? I guess there was a question about problem B. The next number I should choose depend only on the numbers at rest. Well, yeah, because you don't remember any history. You just having the numbers that are available now and choose one of them. Do you have questions about problem C? I guess not. Problem D. I thought that was the second easiest problem in the contest, and somehow it is solved by less than 20 teams. So in this problem, you were asked to check if the number k is provable for n, which means that there is a matching in this bipartite graph. The problem is that n is very big, but it's not a very big problem since we can prove that the answer is yes only for either very small k or very big k. So let's first try to solve the problem for k at most n over 2. Then this set of numbers and this set of numbers do not intersect. And we should check if there is a perfect matching. But let's assume that there are at least 2 prime numbers in this part of the graph. Then both of them has edge only to number 1. They're not divisible by anything else apart from 1 and that number is not present in the left part. So obviously the matching could not exist. So if there are at least 2 prime numbers in this part, the matching does not exist. The prime gap, the distance between 2 consecutive primes for numbers up to 10 to the 18th is less than 1,500. So the length of this segment without 2 primes can be at most 3,000. But actual limitation is much smaller. I think that in the test set, the maximum k for which answer exists is 32. There might be some bigger, but I expect that I'm not much bigger than that. But for the sake of analysis, let's assume that we want to solve this for all the case up to 3000. Okay, then we will just build a graph and run Kuhn's algorithm to find maximum matching. And if it is perfect, then the key is provable. So the most stupid way to implement that would work in k to the fourth, because we have to check all the numbers up to the k and then find matching in cubic time. But actually, the number of edges is only k log k, because for each vertex in the left part, like the edges should go to the numbers that are divisible by z. So we're getting the harmonic series here. So the number of vertices is k and the number of edges is k log k. And also we don't have to run the matching from scratch each time. We can add try the numbers k in increasing order and add new vertices and edges to the graph, and then increase matching if it is possible. So the solution works in k square log k time, which should be fast for k up to 3000. But actually, k to the fourth should be fine too. And yeah, we should also say something about bigger k. Yeah, for big K, now the parts intersect, but we can show that it is always good to match the equal numbers. Suppose that we have done something different. Well, then this number is divisible by this number, and this number is divisible by this number. So this number should be divisible by this number. So we can instead match this and these two equal numbers. So when the parts have intersecting numbers, we just match them and get the problem for k smaller than n over 2. So the whole solution is check k up to some bound, which is proven to be less than 3000, but actually much, much smaller. Find which k are good. And then, yeah, you have to print the answer, but the answer is something, then a lot of zeros, and then the same thing, but reversed. This is small, at most 3000, but actually smaller. And to print this, you can just generate strings that are strings of zeros of power of 2, like in logarithm number of strings. And then the final string is generated just by reaching this by hand, then the needed number of zeros using the powers of 2, and then this part again by hand. The questions for problem D. We have this weird thing going with answering questions for previous problems. Yeah, sublinear binomial coefficients are not required, obviously. But yeah, you could have pre-calculated factorials locally, but that is not needed. You have to calculate this number once. Are there any questions about problem G? Okay, problem E. you were asked to find a minimum vertex cover, but only if it is small. So if it is size at most the size of maximum matching plus 1, and n is up to 500. So the first thing to do is find maximum matching using any algorithm of your choice. I have used Blossom algorithm. You can probably do it with some randomized Kun. We have not even tried to construct tests against it. So when you have the matching, let's first try to solve. We obviously know that the size of minimum vertex cover is at least size of maximum matching, because we have this matching. We have to take at least one vertex on each edge of the matching, so there should be at least m of them. So we have actually two cases. It is equal to m or it is equal to m plus 1. If it is equal to m, then we cannot do anything else other than take one vertex from each edge of the matching. So we have this problem. For each edge of the matching, we have to choose one of the two options. And then we also have these limitations, which has the form either just you have to take this vertex because we cannot take this one because it is not in the matching. Or for this kind of edge, you have to take either this or this. So this is an instance of two-set problem, which can be solved in n squared time, constructed and solved in n squared time. So this is two-set in n squared time. And yeah, we can see that for finding matching, we have spent cubic time. Here we have spent square time, but we have to also solve for m plus 1. But we can kind of do the same, but many times. Like, what changed when we allow one more vertex? So now we still have to take at least one vertex on each edge of the matching. We can either take both vertices from one of the edges but nothing else, or we can take some different vertex that is not covered by the matching. Okay, we have like all of n possible options. For each option, it is again an instance of two-set problem. We do n square more and get n cube solution. You could have get time limit exceeded if you basically if you use some pre-written code for two-set problem. It is probably written on vectors for like to make it work in n plus m time. But in this problem we have basically full graph, and it is better to store your graph as an adjacency matrix. You don't have any pushbacks, so it is very fast in cube. My solution works, I think, less than half a second. So there was a room for making something worse, but maybe not very big room. But yeah, using vectors for storing complete graphs are kind of stupid. Just don't do that. Any questions for problem E? Problem F. We had to sort a permutation using the operation like cut it into blocks and then reverse the blocks as a whole. Instead, we can see the separation as reverse everything. And then reverse each block. And yeah, the size of the permutation was up to 20,000, and the number of operations we can do is 120. So when we say that we are doing these things, we can just forget about the fact that we're reversing everything. Like, it is important for printing the answer, but other than that, like, just always do the even amount of operations, and then this even numbers of reverse everything doesn't do anything. So our operation now is split the permutation into blocks and reverse each of them independently. Okay, let's first try to sort not a permutation, but instead a 0-1 array. So we have array consisting of zeros and ones. We have to somehow make all the zeros go to the left and all the ones go to the right. It doesn't make sense to break the numbers that are already like these two ones should be always together, and that's fine. So we can find these blocks of consecutive equal numbers. So we will get block of ones and block of zeros, block of ones, block of zeros, and so on. And in one operation, we can swap two blocks. Like we reverse this array. Each of the block will be also reversed, but it doesn't matter because they're all equal. So we can do the following. Let's say that our blocks look like this. We can find like groups of 4 blocks, and in each group swap 2 blocks in the middle. Then we will get 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, and so on. If we then again find the blocks and merge them together, we will see that the number of blocks is reduced like almost in 2. So after logarithm number of such operations, we will get all zeros together and then all ones together. And actually it is like logarithm of n rounded up. So now we can round it down. Well, it doesn't matter now.
Sorry, can I have one question?
Yeah.
Well, you said that you swap those blocks simultaneously, but when you choose 4 blocks, how then you can swap those 2 blocks of 0, 1s at the same time so that they end up in this way? Like
well, you may take a block of just 0, then this block, then this.
Okay, thanks.
So yeah, you want to just swap this, but you can also take just block of size 1, and that does nothing. Well, it reverses the block, but it doesn't matter. So yeah, we can sort the 0, 1 array in logarithm number of operations. Then let's return to the permutation. We can partition our permutation using the number n/2. So we kind of changing all the small numbers into zeros and then all the big numbers into ones, and then apply this 0, 1 sorting procedure. After that, we will get all the small numbers and then all the big numbers. Then we can sort both of that recursively, but actually we can do it in parallel because, well, if we want to do some operation on small numbers and some operation on big numbers, we can just write it as one big operation. So yeah, the solution is take a permutation, do a partition with respect to n/2, then sort the resultant 0, 1 array, and then apply the procedure recursively, but do it in parallel. The number of operations will be like on the first step this, then in the next step is this -1 because we have divided n in 2, and so on. So the total number of operations will be 1 plus 2 plus, so plus log 2, which is log 2 times log n, I mean plus 1 over 2. And like, yeah, if we say that it is rounded up, then it is 15, and this number is exactly 120. But actually, we can show that it should be rounded down here. So it is actually even a bit faster than 120 operations. Are there any questions about problem F? Okay, in problem G, you are asked to analyze a game about removing prime numbers. The first thing to notice is that all the primes are independent. So we have actually a sum of games for each prime, and games for each prime are actually like segments where we have this prime number, and all the segments are also independent, because one move is to choose some subsegment of a good segment and then delete it, thus getting these two new segments. So if we find out these segments for each prime, then we will just calculate Grandie values for each of the segments, take sort of them, and get the result. So we have two problems. First, we have to calculate the Grandie values, and then we have to somehow understand what the segments. Grandie value of n is actually n, but you didn't have to understand that. Like, it is easy to show by induction. If we take some segment, we remove some part in the middle, and thus getting the sum of two games. So we have to take source of these two parts. But XOR is at most sum, so all the numbers we can get are strictly smaller than n, and obviously we can get all the numbers strictly smaller than n, so max should be n. But even if you didn't get that, you could calculate Grandie numbers in n squared time by noticing that the set of moves from any position is a superset of moves from the position with smaller n, or just in n cubed time, also fine, because n was small and the time limit was big. So yeah, the actual issue in this problem is how to get these segments. You could obviously factorize all the numbers, and yeah, there exist algorithms that can do that. But I kind of assume that people wouldn't do that because the algorithms are pretty long. You couldn't type it by hand. I guess you could get accepted with some implementation of Pollard, which is not very long. If you did that, good for you. But yeah, the intended solution is different. It does not do the factorization of all the numbers explicitly. Instead, let's say that C is 10 to the 18th. Let's first find all the prime numbers up to a million. There will be million over log C of them. So it is, well, actually, it is about 8 times 10 to the 4th, something like that. So we could find all the factors of our n numbers that are smaller than a million in times time proportional to n times this million log divided by log C. Just for each number, try all the primes and divide if divisible. After that, what we are left with is like all the prime numbers, prime divisors that are left should be greater than million, so there couldn't be 3 or more of them. So our number is either 1, prime, square of prime, and the product of two primes. It is easy to check if our number is a square of something, so check that. 1 is also easy to check. So what we are left with is either prime or product of two primes. And the thing is, we don't actually have to know what are the actual two primes if we just know that it is two primes, and like there could be problems that one of the primes will go farther. So like all of these numbers are divisible by PQ, but then this number is divisible by P and not by Q. But this we can get by taking GCD of these two consecutive numbers, not by explicitly factorizing the number. And if we just get that we have a segment of numbers that are all divisible by PQ, but the numbers are on the left and on the right are not divisible by PQ, then we don't have to know what were these numbers. We just say that, okay, they have equal grain values and they will XOR each other out. So the only thing we have to know is either it is this case or this case, which can be done by checking if the number is prime, for which there are primality tests. And yeah, they're pretty fast, especially if you use 128-bit integers to multiply numbers with big modulo. But you can actually get this problem accepted even without using 128-bit numbers, just by having actually good complexity. Yeah, we have to go faster. Sure. Problem H that was accepted by one team. So the problem was we were given an array, very big one, and also a lot of queries to this array. one query is a segment. We take all the numbers on the segment as a multiset, and then we have to calculate some function which is defined as what is the maximum max we can get from the set if we are allowed to like, let's draw this set on some number line. So the operation we are allowed to do is if we have some number multiple times, we can take one of the occurrences and move it either to the left or to the right. We want to get maximum max. So what is how you can define it more conveniently for purposes of this problem? Well, let's say that we want to get this max, like the max will be 6. So in all of the cells from 0 to 5, we have to get our tokens. Well, then, and there will be no token in cell 6. Then I state that we just had to get enough tokens in this part already. We cannot move anything from the right because we will then place a token in cell 6. But if we have enough tokens to fill all the cells here, then we can actually do that. It is easy to show. So this function is actually the maximum value of x such that the intersection maximum value of x such that intersection of set S with like numbers less than x has size at least x. So the function of the set is the biggest such x such that in our set there are at least x numbers that are strictly less than x. Okay, great. Let's instead write it as minus x greater than 0, greater or equal than 0, and let's then define function small f as x, which is this.
Sorry, isn't it actually an equality? Because
yeah, it is an equality because this function is like discretely contiguous, but it doesn't matter much.
Well, I said when it comes to greater than or equal to x, because we can always extend it if we have greater.
Yeah.
Okay.
Yeah, it can be equality, but we can also write greater or equal, then it doesn't matter. So we define a function like this. So we want to find the maximum x for which this function is non-negative. Okay. It is tempting to write binary search here, but it is not true. Actually, it is not true on samples, but some implementation of binary search can pass samples, but not pass tests, hopefully. So what we want to do instead is we will try to solve our problem offline. We will do scan line on x. So we will change x from n to 0. And we want to maintain f of, let's say that the set for query I is qi. Maintain these values in some data structure. When we find find out that we have a query with this number non-negative, so it is good. We say, okay, then number X is the answer for this query, remove this value from our data structure, and proceed. Like, try again to take out the, well, basically we will take out the maximum value, check if it is greater or equal than 0. If it is, then we have found the answer for this query, then we remove this query and try again. If all the functions are less than 0, then all the answers for the queries that are in that data structure will be less than X, so we decrease X. Okay, how will it look? Like, what happens when we decrease X? We have some occurrences of X in our array. Well, let's say that we have decreased X and now it is equal to X. So it is not, now the functions should not consider this axis as something good, like something that is counted here. So we have to like do -1 for all the sets that do have this position. Like for each position, we will do some kind of -1. The problem is that it is hard to implement. Like we can store our queries as points into G, like left and right border of the query. Then the query for number X is like when this segment contains this position. Well, the left border should be at most position and the right border should be at least position. So we have to like do -1 on some rectangle and then take maximum. It is a hard problem. I'm not aware of any fast solution for this problem. But we don't actually have to like actually do it for all the queries we want. Instead, we can like have this data structure only for the queries that can like conceivably be the maximum. So we will maintain data structure for not all the queries that we have not answered yet, but only for such queries that could be maximum. How can we understand that some query cannot be maximum? Let's say that we have some query and we have some query that like this segment contains this one. Then this is not the maximum for sure. Like this will be at least as much big. So we can maintain the values f only for segments that are not contained in any other query segments. What's the profit from that? Well, if we only consider such segments, then their left borders are sorted the same as the right borders, because otherwise the smaller segment would be contained in the bigger one. On this picture, that would mean that it goes something like this. And we can see that our query is actually a query on segment now. Like if our queries are sorted by their left border, they are sorted by the right border also. And this -1 query will be a query on some segment of our unanswered queries. So we can sort all the queries in advance by the left border. Then we will maintain data structure only on some queries, well, the ones that are not already answered and the ones that are like maximum by inclusion. For all them, we will maintain the actual value of f in segment 3. This minus ones will be just minus one in segment. We can take maximum from the data structure and check if it is greater than 0. But there is a problem when we want to remove some query because we have answered it, because it could happen that we should add some queries because they are now maximum by inclusion. Well, that can be done with one more segment tree and some sets. Well, basically, it is kind of maintaining upper hull of the points. So I guess you'll have to work out the details by yourself, but the main point that yeah, we can maintain data structures that can maintain the set of maximum by inclusion segments when we delete them, and also maintain the functions on them. And overall, this solution works in n plus q times logarithms of something. Yeah, it has a big constant, but the complexity is actually n plus q times logarithm. We have segment trees for values. We have segment trees when we remove some queries because we have answered them. When we insert new queries, there could be a lot of them, but each query inserted in data structure only once. And when we insert new query in data structure, we have to by hand calculate this function because we didn't store it in data structure. So to do that, we will need one more Fenwick tree or segment tree over the array. We have to calculate this value for given x. But yeah, overall the complexity is this. Do you have questions maybe? Okay, problem I, about buying stuff. Well, there is obviously, well, not from the beginning. First, we have to choose the order in which we will buy the things. If we have chosen the set, then we should buy in order of decreasing the value p. Well, because the value that we will calculate is, well, let's say that they count from 0. It will be sum of I times pi, and using rearranging inequality, we can show that this is minimum when they're sorted in decreasing order. So let's sort them in decreasing order in the beginning, and then go in this order. Then there is obviously O of n squared solution by doing dp. We have solved on prefix and have taken k things. We can either take the next thing or skip it, and we want mean cost, obviously. But this is too slow, but it actually isn't, because k
まあ、ビッ
is
トセットだね。まあ、ある意味隣接行列だけど。
thanks for your input. Because number k is actually bounded
これ終わるわ
by.
け
Come on, can you please turn off your microphone? So the number k is bounded because the total our money is bounded by 1 billion, and this thing already will be too big if k is big. Like for given k, we know that all the p's are different, so this is at least k minus 1 minus I, and this sums up to k minus 2 times k minus 1 times k over 6, and it should be at most c. So k should be at most cubic root of 6c plus 2. The actual bound is, well, it is the actual bound, and numerically it's something like, well, a bit less than 2000. So this dp just works in n, well, times this number. So the complexity is n to the cubic root of c, and it passes freely. There are also some greedies, but I'm not aware of any greedies that can be implemented faster than in this time. Like you still have to you can kind of maintain some set of already taken items and then change it by like adding new item and removing some of the older items, but you have to look at all of them. So you have to use the fact that there are a small amount of them. Yeah, the grids may be faster, but the complexity is the same. There might be some solutions using some complex data structure which doesn't use the fact that like does not depend on the value of C, but I am not aware of such solutions. Any questions? Okay, problem J. So we had to change one permutation to some other permutation. And the operation we could do is take a segment and sort it in either increasing or decreasing order. And we have to do it no more than n operations. The solution is purely constructive. With first operation, we will just sort the whole array in increasing order. So now we have 1, 2, so on, n. And then in each operation, we will set the correct number in the last position, last not set position. And we will also maintain the invariant that, let's say that we have already fixed all of that. If we will go from right to left, each number we see is either current minimum or current maximum. So if it is maintained, then it is easy to now fix this number. We know what we want to set here. Let's find this number and take this array. This number is either minimum or maximum on the segment. So we can sort it in either increasing or decreasing order and put it in the last position. And then it is easy to see that while we are going here, all the numbers will be either minimums or maximums. And when we continue to go to the left, it remains true, because like we can say that our property is that each such suffix is a segment of not fixed yet values. So when we somehow rearranged this segment, it is still true for all the suffixes that are longer. So if we do that, the invariant is maintained, and yeah, we will be done in like one operation in the beginning plus n-1, n-1, because if we fix all the numbers but the first one will be fixed automatically, and this is exactly n. Any questions about problem J? Okay. Okay, we have 9 minutes. I guess we'll have to skip problem K. If we will not skip problem K, we will not come to problems L and M. Let's first talk about problem M. It was supposed to be the easiest problem, kind of a joke problem. So you were asked to calculate some recurrent sequence. The number A0 were given explicitly. And n+1 is like discrete logarithm of a n modulo some number m, which is big, using the base g, which is primitive root. So by this definition, we can deduce that an is actually g to the power of n+1. So calculating this is hard, but calculating this is easy. It's just binary exponentiation. So it is hard to go left to right and calculate the elements, but it will be easy to go right to left. If only we knew the last element of the sequence, it will be easy to restore it from the end. And by sheer luck, the last element of the sequence is given in samples. So yeah, that's the whole solution. I guess you could get time limit. There are some ways to not get time limit. The easiest one is just to multiply numbers using 128-bit arithmetic. The other way is to actually get better complexity. Because we only calculating powers of one element, we can pre-calculate its powers up to some like b, and then calculate its powers in form b times something, and then do the same for b squared. So if we choose b equal to a million, all of this can be done in 3 times a million, and then you can calculate any power in 3 operations. So you have to do that a million times. So that's also this number of multiplications. But if you could not do neither this or using just faster multiplication, you could pre-calculate some values locally so that you don't have to run through all the million values. Questions for problem M? I have already sent the PDF of the solutions in the chat. Not the Zoom chat, but chat in Telegram. Is it possible to solve without optimization? Like what optimization? There are 3 optimizations. Any one of them is enough to accept. So you can solve it without any 2 of the optimizations. And problem L, about playing in the casino. So first thing you have to get is that the answer to the problem is this value. You can either deduce it from, it is not hard to come up with quadratic GP, and you can calculate some values on paper and get that this is answer. But there is actually a more general and more beautiful way, I think. You can say that, it is written in the statement that you can't bet on both options in at once, but you actually can, because if you bet some x on one option and x on the other option, it's the same as don't do anything. So instead of betting some part of our money on one of the options, we can always split the money fully into options and proceed with winnings. Then it is easy to see that in any option, in any position, we can just split all the money, and we can actually see that for any order of events, we can actually take some part of initial money and always bet this money and all the winnings on this option. So we have to split all our initial money in some parts corresponding to the order of events, and the number of orders is this. And for each of the this option, we will win this amount of money. So the best way to do that is to split it equally, thus getting 1 over this binomial coefficients times 2 to the power of b plus r. So this is the answer, and then the actual problem starts. The actual problem, how to calculate it precise enough. So b and r was up to 10 to the 13th, and we were asked 10 to the minus 6 precision, but if the number is very big, bigger than a billion, we don't have to calculate it actually. So yeah, this is something with factorials. Let's look at it. We could use just Stirling approximation for logarithm, but it is bad because if we just calculate logarithms of all these things, then logarithms of numerator and denominator are of order b log b, but the logarithm of answer is of order log b. So you will have to take a difference between not precisely calculated numbers of this order, and the difference is very small. So this doesn't work well. So instead, we will try to use Stirling approximation for b equal to r, and it works better because everything will cancel out. You can just look at the editorial, but yeah, this thing is square root of p times b times 1 over 8b plus big O of 1 over b squared. So we can calculate this very precisely. And then we can, let's assume that r is bigger than b, we can increase value of r by 1, precisely recalculating our value. And actually, if we do it for long enough, and long enough is square root of b times logarithm, like for any square root of b operations, we will increase the value 2 times. So after logarithm of such blocks of square root of b, the number will become greater than a billion, and we don't have to print it. So yeah, that's the solution. And I guess we are done. You can read the editorial of problem K in PDF. Thanks to the live team, we are done. We can proceed to the awarding ceremony.